Hey guys, it's Miss Miller and we're going to talk about acceleration today, or continue our discussion on acceleration. Just a couple notes here. First of all, let's define acceleration. Our definition is acceleration is the rate of the change in velocity per unit time. So, being a rate of change, we'll talk later about how a rate can be related as a slope of a velocity graph. The equation for acceleration, or your go-to equation, our number one equation, is the acceleration is change in velocity, so final velocity minus initial velocity per unit time, so over time. Now, this time is actually a duration of time. So if you change velocity from 0 seconds to 10 seconds, your time would be 10 seconds. However, if you change velocity from 5 seconds to 10 seconds, then your time would only be 5. So let's note that this time here, t, is a duration. It's not just, it's not always your final time. Now, let's look at a couple visual examples here. Let's say we have an object. I'm going to represent the object's speed by arrows. So the length of the arrow will basically represent how fast the object is traveling. Here we have an object moving, and each arrow is going to represent like a unit of time. So here we have an object that's, we would say, is moving at a constant speed. Now, why is it moving at a constant speed? Well, that's because if we look at each section, if we look at where that object is for each second, it's covering the same amount of distance in the same amount of time, which indicates that it's going at the same velocity. Now, an object that is accelerating or changing its speed might look something like this. Notice my arrows are getting longer. This would be an object undergoing constant acceleration. We know it's accelerating now because in the same unit of time we covered greater distances. So this is where the object would end up after 3 seconds. Okay, notice each distance. Let's call this one D1, this one D2, this one D3, D3 here. D3 is greater than D2, which is also greater than D1. So the distance that I cover per unit of time keeps increasing. If it keeps changing like that, whether it's increasing or decreasing, if your velocity keeps changing per unit of time, that means you are accelerating. So, acceleration is a vector, just like velocity is a vector, which means positives and negatives matter. We need to understand the sign for acceleration, whether we're going to call our acceleration positive or negative. So, the cases where we have positive acceleration are, first of all, if we're speeding up to the right. And if we were speeding up to the right, I'm going to draw a velocity and time graph to show you what that would look like. This is the positive velocity, this is the negative velocity, and this line right here would represent a 0 velocity. Now if we were speeding up to the right, I would be increasing my velocity from 0 to some number in the positive direction. So if you notice, the slope of this, rise over run, that slope is positive, which indicates a positive acceleration. Remember, we said acceleration was the rate of change of velocity over time. So the slope here is the change in velocity over a change in time. So that slope represents our acceleration. So this is one case for positive acceleration, speeding up to the right. I'll draw arrows to represent that. So there are my arrows speeding up to the right. Another case for positive acceleration will be slowing down to the left. Okay, here's another velocity and time graph. Now, if you're slowing down, you're starting at some speed, and I'm going to have a negative velocity to begin with because I'm moving to the left, and I have to approach 0. So this line right here represents my motion if I were to be slowing down to the left. And if you notice, the slope, however, the rise over run, our acceleration, would still be positive. So if I were to draw arrows there, I'm slowing down to the left. It's going to look like this. My sign for acceleration is positive. On the flip side of that, we can also have negative acceleration. Okay, so in a problem you would say A equals negative whatever to solve the problem. Well, basically it's the opposite. So we have, we could speed up to the right, but if we slow down to the right, which would look like this, then we would have a negative acceleration. And slowing down to the right means I would be going from a positive velocity and approach a 0 velocity. So notice that line there, the slope of this line, ends up being negative. So that gives you a negative acceleration. And opposite of slowing down to the left would be speeding up to the left. So that means my arrows start over here and get bigger. We're speeding up to the left. And on a velocity graph, positive, 0, and negative, that's time, that's velocity. We would start at 0 and get bigger in the negative. Now that negative is just direction. It just means that you are moving to the left. And again, if you look at the slope, our rise over run is negative, so that means the sign of my acceleration is going to be negative. So when we go to solve problems, our sign convention is going to be very important. You're going to have to figure out, should I label this a positive acceleration or a negative acceleration? Okay, next up I'm going to give you some equations that will help you solve acceleration problems, and this is basically going to be your toolbox of equations. So our mathematical model for acceleration is given by this. We have our first equation is delta x equals 1/2 a t squared plus vit. Our second equation is vf squared equals vi squared plus 2a delta x. This is our first equation that I introduced you in the beginning of this video over time. And finally, we have a new equation. If we are constantly accelerating, our new average velocity is our initial plus our final over 2. Now in the videos before, when we've talked about average velocity, we just said displacement over time. We couldn't add the initial and final and divide by 2 because we weren't necessarily moving with a constant acceleration. So this equation is only used, or all of these equations are only used if there is constant acceleration. So let's just name these our constant acceleration equations. Now, we're going to go through and we are going to define all of these variables in the next few minutes. So, first of all, let's look at delta x. Delta x equals our final position minus our initial position. Okay, x is change in position. So that's where you're at. Our units should always be meters. Okay. or those are the SI units. Sometimes a problem will allow you to use kilometers, but for acceleration, 9 times out of 10 it will be meters. A, obviously, A is our acceleration. We will never deal with a change in acceleration because in physics, or at least this class, we only deal with constant accelerations. You don't get into changing accelerations unless you're going to take mechanics in college. And of course, if you go on to take mechanics in college, you can email me and ask me all about changing acceleration, but we're not getting there yet. Let's see. So T, obviously, is time. Please remember, this is a time duration. I mentioned before, in most cases, our time generally starts at 0, but if it doesn't, if we're talking about something going from 2 seconds to 5 seconds, then the T for this equation would be 3 seconds, not 5. Okay, so this is a time duration for which the acceleration is happening. VF is a final velocity. Okay, the units are meters per second. Okay, remember velocity is displacement over time. Also be careful, our velocity, the sign of the velocity matters. Okay, it's either going to be positive or negative. If we're moving to the left, or if your object is moving down, then you'll have a negative velocity. VI represents initial velocity. That's where you start. Let's say an object started at 20 meters per second and went to 30 meters per second over the course of 5 seconds. Then my initial speed would be 20 meters per second. My final would be 30 meters per second. And my time would be, I'm not even sure what time I just said. But it'd be whatever I just said for T. Maybe 5, I think is what I said. I'm not sure. But that's what your T would be. So VI, alright, and VAVG is average velocity, in case it asks you for average velocity, only under the terms that we are constantly accelerating. Okay, lots of information thrown at you. From here, you should watch the derivations video. It's a boring rendition of the history of these equations. It's basically, we start at the most basic function we have of an object accelerating, and we create all of these equations. So it's pretty cool. And then after that, we will work on some practice problems. So let me know if you have any questions. I hope you have a great day. Talk to you later.